Alzheimer's is a neurodegenerative disease. 46.8 million people worldwide were living with dementia in 2015, and the number of new cases is expected to double every 20 years. The total estimated worldwide cost of dementia in 2030 will become $2 trillion. Alzheimer's destroys memory, is associated with old age, and diagnosis is made by studying thinking changes and sometimes brain imaging. So what can we do to improve the condition? Making a correct and early diagnosis can be helpful. When clinicians are asked what would make the diagnosis more efficient, the third most common answer is an algorithm with clinical and brain imaging input. The state-of-the-art algorithms to perform classification of Alzheimer's from brain scans use ResNet, a type of CNN. Let's try to improve our ResNet to achieve higher classification accuracy in the task of healthy individuals versus Alzheimer's. By analyzing the state-of-the-art, we see that the information about where medical doctors focus may help deep learning models yield better results. We saw that for glaucoma and other diseases. Let's test this hypothesis. The eye gaze dataset was created for our experiments using an eye tracker, while an expert clinician made Alzheimer's diagnosis by looking at PET scans. 3D PET scans like this one. The doctor was making a diagnosis by analyzing slices of the brain scan. Meanwhile, the Tobii device was capturing the fixation points on the screen. In our dataset, we possess more than 1,000 scans from a little more of 400 subjects. We have Alzheimer's scans, scans from healthy individuals, and scans from the intermediate state called MCI. Additionally, the same expert physician has manually identified 12 regions of interest. These regions of the brain are considered to be the most relevant for Alzheimer's diagnosis. Using the eye gaze and regions of interest, two approaches were followed. The first method inserts the average attention map into the ResNet, and for comparison an alternative inserts regions of interest. The second method supervises two alternative networks to learn the underlying pattern between scans and the corresponding attention maps, which are inserted into the model. Finally, for comparative purposes, the first baseline is defined, which is a standard ResNet, and the second baseline is composed of a ResNet with two traditional attention mechanisms. Our methods perform better than most systems for Alzheimer's disease working with PET images found in the literature. Nonetheless, there are shortcomings like the small eye gaze dataset and the improvements being only marginal.